if he wants to hear it, he can hear it. What do we know about a limit right now?
Do you want like the definition
Um,
or what I think it is?
what you think? I want to know what you think it is, yeah.
Okay, it's like when the two lines are coming to a point.
Okay.
Maybe not like a point, like coordinate point, but they're going to a place on the x-axis.
Okay, so that's about as concise as you can get, right? So she's saying two lines and she pointed like this. And so, like, use a little bit more terminology, like what is going, like when you're doing that. Well, so like left and right is what I'm saying, right? From the left and the right, they're both approaching is good. Some value. Now, like she said, it doesn't have to be a value there, but they both have to go to it. And if they both go to it, then you can say that what?
There's a limit.
That limit exists. And then vice versa, if I say, yes, this limit exists at this point A, what does that tell you? That the left and the right also go to point A. Okay, or go to the same value as the original. Okay, so that's basically really all you definitely need to know right now. But like even if we back up like a step further, what's the idea that we're doing with this limit?
It's like where, so like if at, like on a fraction, like the denominator can't be zero, and so like you're kind of trying to find like that instantaneous velocity or like that like number where there's not really a value, but.
Okay, so yeah, you got a couple things going on here, right? Like so, that is totally, absolutely related when we're talking about the slope of a secant line. And then if we shrink it all the way up so that's instantaneous, and that's kind of where I was going, is like, right, we're shrinking up that interval until it's just 1 point. And so then that is completely 100% related. They are exactly the same thing as the slope of the tangent line there. So the tangent line is the same as instantaneous velocity. And again, the velocity is our generic word right now. It's actually a specific word, but this is going to be true for any rate of change, right? Like it's the easiest one to think about. And so that is very, very, very important to keep in mind. Average is a secant line. Instantaneous is a tangent line. Okay, slope. We're still talking about slope. And absolutely, it doesn't have to be there for this to work. Okay? But we are narrowing in on it. We're getting super, 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 super close. Okay, so if you guys get all of that, then you're doing very, very good. And so that covered like basically everything. All right, so then let's do this. Then we can talk about 25 because we should talk about 25. And then we're going to do a couple other things together. And then I said this is a 3-day lesson. And I think we can save a day, which we are trying to save some days. Ideally for the end of the year, but also so that we're comfortable going through like these progress checks. Because for instance, in this chapter, there are 3 multiple choice progress tests and 2 free response progress checks. Okay, so that's a bunch. I'm not going to have, we will not be able to do all 5 of those in class. Because we only, in our pace, we only get 3 days for testing and stuff like that. So at least 2 of those will be take home. For sure, one of the free response, because I would prefer you guys to think about that one and work through it probably even together. Okay, those are all the grades. So we're gonna save a day here, and that'll get us maybe even 4 days because we also have to do a chapter test. Okay. And so then we are over the weekend. The way we're gonna save a day is I got another one of the ones on the AP College Board. There's 18 questions, and it's all about this section. Okay. And so then you got the whole weekend to take care of that. And it should open here in about 15 minutes, so we might even be able to look at it before you guys go. So on this, explain the meaning. Firstly, how is that read? Explain the meaning of this. How's that read?
X approaches A.
Yeah, okay, that's fine. So right, it's, your option is the limit as x approaches a. That's usually how I do it. Of f of x equals this L. What is L? A number. And of course f of x is any function. Alright, so then explain the meaning, like, so we've kind of already done that, right? As we get closer and closer to a, from the left and the right, this function appears to be going to this value L. Okay. True or false? When the limit as x approaches a of f of x exists, it's always f of a.
No.
When would it not? Like, how would that not happen?
Wasn't that saying like when there's like this point up here that's f of a,
Yeah, you're pointing at the
like number 7.
yeah. Okay, so is that okay? Very, very important, right? Does not have to be there. And in fact, kind of like something we were just talking about, usually we're not looking at the ones that are there. Usually we're looking at the ones that aren't there, because like that's kind of like, whoa, what's going on here, okay? Explain the meaning of that first one, number 3 there, that's with the plus. Coming from the right, right? Coming from the positives. And then of course, number 4, coming from the left, with the subtraction sign there. Okay, so now number 5, this is a good question. If from the left it equals L, and if from the right it equals M, where they are finite real numbers, how are L and M related if the limit as x approaches a exists? Right here.
Doesn't it not exist if they're not both L?
So, okay, so they're saying, but, so then what is the relationship between L and M if it does exist then?
They're the same.
Is that okay? Then L and M have to be the same thing. And then potential problems when you graph.
But like it doesn't always show where it doesn't exist.
It doesn't show where it doesn't exist. It doesn't show, like, you know, it's not super accurate. Maybe you have to zoom way in, which is a good, like, segue into number 25 down here. Okay, so how many did everyone try number 25 or did like okay? Okay. All right, so then we have to say again, even if it didn't say the technology one, you should absolutely be graphing these. If you want to graph it on your graphing calculator, good. If you got Desmos handy, good. Go ahead and graph this function. And so put it in your, so that you can see a table. And then you can enter those values in on the table. So go ahead and do that. And then tell me what happens when you enter those in. And this is doing part A, basically. Yeah, go to table set. You want the independent to be asked. And again, when you're entering these in, yeah, so you get the table. And so when you're super zoomed out, like you leave the window the way it is, it doesn't look like there's a whole bunch going on. But you can actually enter in those values. And if you want to see it a little bit better, like what they're showing you, right, then you got to go way in, yeah. I think you could enter it, we'll zoom in for you. Like it almost jumps. Like so he zoomed in once and it basically like skipped everything.
There we go.
Yeah, there you go. And so then they pick the specific values for you.
For the first 3 up here, one negative.
Yep, that's exactly what it's doing. And remember the table kind of does some weird rounding.
Oh, I have not zoomed in.
Looks like a weird barcode.
Yeah, right, yeah.
Oh, okay, I understand now.
Okay, and I think you guys, it looked like you guys were getting like decimals on some of those entries.
Yeah, it like changes into decimals when you type in like the whatever with pi.
But the first ones didn't.
No, mine all did.
Oh, that's something else. Okay, yeah, okay, so it should be rounding it, okay. So then, what is going on when we're bouncing, right, 2 over pi, 2 over 3 pi, et cetera, what is the outputs being?
I went from 1 to negative
1, right, they go 1, it's 1, negative 1, 1, negative 1, 1, negative 1. Okay, so then why does the graphing calculator have difficulty plotting this? Like, cause like when I was watching Trevor, he zoomed in, like the first thing you saw looked like fairly, nothing much going in. And then he zoomed in once and it was like it just skipped over it for a second. So then like, why is the calculator not able to do this? Like,
I'm not sure. Because it's so close together.
yeah, like, right, we're
Like
really
the
getting super
frequency
close,
is-
and it keeps bouncing, right? Like, it's just going bouncing, and we keep getting closer and closer, it just keeps bouncing. So they can't even draw it, that's how, until you zoom in a little bit. Okay? So then,
What's the best way to zoom in on a graph?
Well, he did, yeah. Yeah, if you do that, and then you can keep hitting enter and it will keep going in. Now, the only problem with doing zoom, and again, this is why Desmos is a little bit nicer. The problem with zoom is, I guess zoom on Desmos does the same thing, but everything shrinks at once. So like, it might be a little bit better to do a window on some of these things too.
Why does it get like more frequent and then slow down?
Say it again.
Why does it like slow down? Like the bouncing doesn't go as fast like on the outside.
Yeah, so that has to do with the 1 over x part of this. So like, it really starts leveling off because we're putting in like 1 over x. So if we're putting in like these fractions, then really we're putting in like some giant value. And so then as we get closer, when we're going really far away, it's actually putting in a really small value. And then when we're getting really close, all of a sudden they're really big values, and so then they're jumping really, really, really quick. So again, this is why this, sometimes the graphing calculator can't handle these things. So how can we answer part C here, right? What do you conclude about the limit as x approaches 0 of this function?
All exists.
So she's saying it doesn't exist. Why?
My reasoning was there's values of 1 and negative 1.
Yeah, right. And every time you move a little closer, it goes to a different value.
Yeah.
So the whole idea of a limit is as we get closer, it actually gets closer to some value,
Same.
right? And so as we get closer, it's actually like less likely it's going to something, right? Does that make sense? Okay. So we feeling okay?
Yes.
All right. All right, so up here at 27. Right, the value of this, and yeah, graph it if you want to. Right, part A, the value of, as x approaches 3 of this does not exist. And then I'm going to say to graph it, and then I'm going to say something about it. Kind of refer back to some pre-calc stuff that we talked about. And like while you're graphing it, is this the graph that you expected it to be? Right, you're saying, no, this is not the graph you expected it to be, right? What did you expect it to do? Not a line, yeah, basically not a line, because it's a rational function. Okay. Now is there, okay, so did you want to answer this first? Okay, so you should be graphing these things, okay? I knew this was going to be a line, and this goes back to what we talked about in pre-calc. When you have a rational function, if you can, so firstly, x cannot be 3 no matter what, right?
Correct.
What happens if we factored the numerator? What would that factor into? X plus 3, x minus 3. And then you could cancel the x minus 3s.
And it would just be x plus 3.
And so then it's just x plus 3 left, which is what the graph is. You had this graph going through that was x plus 3. But again, and it probably doesn't show it on there, but there's a hole there at 3. Okay, because 3, it can't be 3 no matter what. So again, so when we talked about rational functions in pre-calc, we made this statement that was for you guys, and so we didn't spend a lot of time on it, but it was for you guys. If you can cancel the denominator, then you have a hole. If you can't cancel the denominator, that's where it starts getting like, you would have like, this kind of stuff where it would be like maybe, right, you'd have all these weird things because it was rational. Okay, and then maybe, it even got crazier, right? Like we remember these horizontal asymptotes that we would have. And so maybe it even looked like this. Okay, so when I saw this, when I look at it, right, like I knew that rule. So I was like, oh, okay, so the x minus 3 is going to cancel. So then it will be not what you expect it to be as a rational function. So I'm not saying you should know that, but like hopefully that's something that you keep in mind, right? But you should absolutely be graphing these things until you feel comfortable about that. All right, so then if it was one of these, right, if it was one of these, then probably it does not exist. But does the limit exist there?
No, because like if the launch is going up, like if minus.
Because what's the graph? The graph kind of looks like this. Like it looks like this, basically. Is that what it looks like?
Yeah. I would say yes, because even if there's like not a point there, that's where the 2 points are.
Yeah. So this is all about is it going to the same place from the left and the right? Okay. So since it is, yes, it does exist. Now they're not asking what it is, but is that okay? All right. So again, everything right now is you want to have the idea of what we're doing with the limit, shrinking it up. You want to know that the slopes are the same as the rate of change, velocity or whatever, average, depending on instantaneous. And you want to know that it better be going to the same place left and right for it to exist. And of course, like on that one that we just did, 25, it has to be going to a number. It can't be bouncing all over the place. It actually has to be going somewhere. All right, so part B, the value of this function, so the value of this limit is always found by computing f of a. Okay, and that's that same kind of question again, right? No. The value of this limit does not exist if f of a is undefined. What's that?
The limit exists.
It still could exist, right? It doesn't matter if f of a is there in the right place, if it's somewhere else, or if it's even there. It doesn't even matter, right? F of a is not what we're talking about, right? We're talking about all getting closer to f of a, or a, I guess. This is a good one. The limit of this is 0. The limit of this is 0. I'll make sure before I say.
If there's no left-handed limit, is there even a limit?
So, right, okay, so we get to this endpoint thing like you asked yesterday, eventually. Abby, what did you just say? Because this is like two different ways to look at this. One is the way Dina just said, and then Abby.
Since it doesn't have the plus and the minus, that means you're looking for the line going both directions, so it's not that much.
Okay, so then, no, this one does not exist, but then Abby said she's like, no, because there's not a plus. Right, so this would be an absolutely true statement, right? If we had just like that little plus right there. I can't draw it.
Coming from the right.
If it just said, does the limit coming from the right exist, or is it zero? Then you'd say, yeah, it's zero. But since they don't give that, then they are saying from the left and the right. And so then, there is no left, so then we say, no, it does not exist, okay? So yeah. And then go ahead and I would graph that one. I would love for you guys to know what cotangent looks like, but go ahead and graph it and take a look. And you may want to, this is another calculator thing, you may want to go to table set. And then the change table, right, the triangle table, it says 1. If you want, change that to like pi. No, be careful. This is like notation. That's inverse. You gotta, actually put 1 over. Or you can put it all in parentheses and do the -1 if you want to do that. You know what I'm saying?
Okay, actually,
But that's a notation thing, so no, don't do it. Oh, yeah. So you can do 1 over, yeah. But it's cotangent, so it should be 10. Is it cotangent? I think it should be the triangle one. 'Cause that's the change in the x value. I think that's, actually, you know what? Better, sorry, I did that back. Better is to just go to the window and change the x scale. Go to the window and change the x scale to like pi. Sorry, it might do the same thing, but change the x scale to pi. You might want to change that other one to 1.
yeah.
I think that's just referring to the
There are a bunch
table.
of errors in the table. I don't know if
Oh yeah, so why is there a bunch of errors in the table? Yeah.
I don't know if that was because
No, there should be some errors in the table, but why?
it's like stops. But
There's a bunch of horizontal asymptotes, right? There's certain places where we'd be dividing by 0, so there still should be some in there. But if you change your scale on your window, it should match up, and you should be able to tell where we're doing pi over 2.
yeah.
So then, do we have a? Do we have an answer of? Is it going to 0 from both sides?
Yes.
So then, it equals 0.
Yes.
So is this okay? Okay. So any questions so far? Alright, so I like doing these, which means I would know how to do them if I was you. We're looking at 28 and 31, 28 to 31. Oops. Alright, so they're giving us some information, and we want to sketch it. So, should we do the first one together? Yeah? Alright, so then, let me shrink that up. So we're going to do 28. Let's just do 28. Eh, boy. So give yourself a corner plane, get some, how far do we gotta go? We got some 1, 2, 3, stuff like that. Now, I wouldn't worry about the Y scale. So let's start with some stuff that we definitely know. And so we have some statements that we can definitely start with. For instance, we know that f of 1 is 0, right? So we can, f of 1 is 0, so we can start like that, yeah? And we know, oh, I guess we do need some y. So then we also know that f of 2 is 4. And we also know that f of 3 is 6. Oh, I need more. All right, so we definitely have those. And then we have, right, the limit as x approaches 2 from the left is negative 3. But as it approaches the same thing from the right, it's 5. So the limit doesn't exist, but what's that graph going to look like? Huh?
It's piecewise?
No, what we're going to, well, yes, it is piecewise, totally piecewise, yes. So right, it says, so let's start with the first one. So, right, we're looking at this value right here, right?
Draw your open circles at 2 and -3 at 5.
So yeah, one of them, so it doesn't specify, so you can make it either one. Okay, but then they're saying, so as we get closer to x is 2 on the left, it goes to negative 3. So as we get closer, so that's negative 3 right here. Right, so I'll put an open circle there. And so then it would be like something like this, yeah? Could be anything, could be a curve. But as we're coming from the left, that's where it's going. And then they don't tell us anything else, so you could do whatever you want over here, right? Could be doing anything. And then, like he said, then it says, well, when we're getting closer to 2 from the right, it's going to 5. So I guess we should have both open circles, because, right, we had this defined right here. And so again, this could be doing anything you want over here. Is that okay? You want to do another one, 29? Because you guys got to do 29 and 31. Should we do another one, or you want some time to do it, or what do you guys want to do? All right, why don't you guys try one on your own?